Hello and welcome to Channels for Nextflow podcast. You are listening to episode number 24, going out on October the 9th, 2023. My name is Phil Yules. I'm a developer advocate at Secura Labs and I'm talking to you today from Stockholm. Today with me I have Chris.
Hey, Chris. Hi everyone, I'm Chris. I'm also a developer advocate at Secura Labs and today I'm joining you from Vienna.
And today with Chris and I in the studio we have Ben Sherman from Secura Labs. Hey Ben.
Hey everybody, Ben here again, hitting you up from Austin, Texas, United States of America at 8:30 in the morning.
Yeah, you're doing the hard work for us all, Ben. Appreciate your early alarm clock. Supporting those of us based in Europe. the truth of working remotely. Early starts.
I think I'm still the only American engineer on the team. We've got a big sales team now in the U.S., but I like to say that that Secura's Texas branch is just my home office. So you ever guys
representing. Yeah. Anyway, we've got some good stuff queued up today. Today we're talking about, most of your episodes, Ben, have been split into kind of language updates and runtime updates for Nextflow. And we talk about the pull requests which are in play, things which are kind of in development to come soon to Nextflow. Today we've got runtime updates and we've got some stuff all about resources and kind of how Nextflow interacts with the underlying system and makes use of requests resources and makes use of what's available. Do you want to kick us off here? I've got first item on my list I can see is fractional CPU requests. What are we talking about?
Yeah, so this was a request that came from, I believe this came from a Nextflow user who was using Kubernetes, and they wanted to be able to do something like request 0.9 CPUs or 1.1 CPUs or something like that. I think the argument was that if you say you had a node with 8 CPUs and you wanted to run 8 tasks on it, if you gave each task like 0.9 CPUs instead of 1 CPU each, then that would give you a little bit better performance because then the tasks would have a little bit more leeway, if one task needed a little bit more and the other one needed a little bit less, so on and so forth. But also just more generally, like it can be useful if you have a bunch. This kind of also ties back to if you have a pipeline that has lots of these little short running tasks or really lightweight tasks. This would apply also to like the local executor where it's like, well, maybe I can run like 1,000 little tasks and give each of them like 0.1 of a CPU. Rather than request 1 CPU for all of them, which right now is the minimum. And then, Nextflow's only able to do 8 at a time instead of, 1,000 at a time. This is, I think in the grand scheme of things, it's a relatively minor thing. But it would also be nice to have. So basically this feature would just allow you to specify non-integer CPU requests like 0.5 CPUs, 0.1 CPUs, 1.5 if you wanted to do that. There's only certain compute environments that support this, right? So the local executor could do this. And Kubernetes has this concept as well where you can request milli CPUs. So you could say like 500 millis when you request the task in Kubernetes. And that basically corresponds to for every second of CPU time, you're getting 500 milliseconds. So that's how it's basically like a timeshare. If you request half a CPU in Kubernetes, you're getting half that CPU time when it actually runs. So the CPU would be switching between you and then something else. That's how they do it.
Yeah, you preempted my question there because I was about to say like call me old school, but I think of CPUs as being integers. You have 1 or you have 2, but it doesn't really make sense to me to have half a CPU. But I guess, yeah, like you say, if you're talking about kind of an allocated amount of time on a given CPU, then I can sort of see how you can split that up. So you're basically over allocating tasks and saying, how right. Does the scheduler deal with that? Do you know?
Well, so you're not necessarily over subscribing the CPU you're just able to provide more tasks. You're able to split the same amount of CPUs among more and more tasks. So instead of having 8 tasks with the CPU each, for example, you could have 16 tasks with half a CPU. And the idea is that if that task was only ever using half a CPU anyway, in the first place, that means currently you could only, get half the throughput as half the ideal throughput. So this could allow you to, in situations like that, actually fully utilize your CPUs if you have tasks that aren't fully utilizing individual cores. Now, I don't know how often this really comes up. A lot of bioinformatics tools probably are pretty good at, fully utilizing the cores you give them. It just depends on the tool, right? Some of them might be more memory intensive and more lightweight on the CPU side, or more IO heavy. Maybe they're doing lots of network transactions and not so much of like CPU sort of stuff. So, in situations like that, it can be useful.
And I guess the heart of my question before is like, who is it that's allocating the CPUs? Is it Nextflow that's saying when tasks should switch between CPUs, or is it Kubernetes, or is it just up to the tools themselves?
So I think the way that Kubernetes works under the hood is that it's actually using Docker's mechanism, or if it's not Docker, like run C or whatever container runtime it's using. These container runtimes also support this concept where you can request a certain number of CPU shares when you run a container. And then those CPU shares get translated into this like shared CPU time. So I think it's actually something that's ultimately supported by the Linux kernel. And you know how Linux has this ability with to virtualize over itself. So it's something with that. Unfortunately, I haven't spent a lot of time at that level, so I don't really know the details of how it works. All I know is that that's the interface that Docker provides to you in doing the time shares. As for the local executor, the local executor doesn't actually do like hard scheduling. It just it knows how many CPUs and how much memory you have, and it knows how much task requests. So it just kind of keeps a little ledger internally, and it's just so that it doesn't launch more tasks than there are resources available. So in that case, it's just sort of launching tasks. And it doesn't really tell the operating system, this task is only allowed to use half a CPU, right? So in that situation, a task could request half a CPU, but then actually end up using 8, and Nextflow would be none the wiser. But in that case, it's basically just everything is handled by the operating system itself, right? So again, that comes down to if you know that you're going to launch a bunch of these tiny little local tasks, and that on average they use only about 10% of the CPU time, then you should in theory be able to allocate many more tasks on that basis, and just know that when the operating system receives all those tasks, it's all going to sort of work out, and they won't crowd each other out, right?
So this goes quite nicely together with some of the other features we've been shipping, which we've talked about in previous episodes, like task batching and task arrays and stuff, where Nextflow is getting better at handling very many small tasks.
Yeah, this would be like an alternative to having to do task batching in the first place. Is, well, if I could just request a smaller CPU fraction for all these tasks and just let them run, then maybe that's all I need. Now, on something like AWS Batch, you're probably still going to want to go for the task batching, right? Because, even if you could submit a bunch of AWS Batch tasks with, half a CPU, you still have all that VM startup and teardown time, right? So, in different environments, different strategies might be more appropriate. Also, regarding AWS Batch, there's this other thing called Fargate, which is sort of an alternative to Batch, supposed to be ideal for lightweight tasks, and it'll actually allows you to request. So in AWS Batch, the minimum request for a CPU is 1 CPU. You can't request less than that. But with Fargate, that restriction is lifted. So with Fargate, you could request half a CPU or a quarter of a CPU, I think. And that also, AWS Batch is using Docker under the hood, that CPU shares concept. It's using that exact same thing to facilitate that fractional CPU. So that's not really something that's possible right now. We're looking into supporting AWS Fargate as like execution backends where you could submit tasks with Fargate, because I think then you would get the VM startup time is much lower, I think, in that case. Again, I don't know a ton about Fargate. I just know it's something that we're looking into. If we manage to get this fractional CPU thing working and also Fargate support, then that could be another interesting sort of a niche use case, but something where you could maybe launch a bunch of really small tasks, and do that efficiently without having to do something like task batching. But we'll see. This is it's still in a very much of an experimental stage. This fractional CPU PR has been in review it's been basically done for a long time. It's just, I think Paulo and I are both, we're still a little bit unsure about any unintended consequences that might come from it, because now suddenly the CPU request can be, a fractional value, whereas before it was always an integer. And so there might be other systems that are expecting integral CPUs, and now they're getting these fractional requests, and we got to figure out like what's the best way to deal with that, like in Tower, for instance, but also even like when you're in a task, how in a Nextflow process, you can reference task.cpus to get the number of CPUs. And oftentimes people will do that to say, like, if your tool has a command line argument for like the number of threads that you want it to use, people will just pass in the CPUs. Well, what do you do when if the CPUs is something like 1.5? Now, I don't know when somebody would want to request 1.5 CPUs. I think it's more likely you would be doing something like you would be doing like 0.5 or 0.9 or 0.1, something less than 1. But in any case, like, what do we do there? Do we just round it up, round it down? Do we make it null? Do we just pass it as it is and just let the user deal with it? I think that's one of the remaining ambiguities that we're grappling with before we actually merge this feature.
I feel like this is a good example of one of those sort of requests where it seems simple. It's just like changing how Nextflow kind of requests resources, but suddenly we were talking about all these unintended consequences. I'm grilling you about how the Linux kernel works. Like, the detail suddenly starts kind of exploding.
Yeah. Cool. I also wanted to mention, like, just piggybacking off of this feature, there's a related request to have the ability to have a separate request and limit for your CPU request. This is really only relevant for Kubernetes, I think. Kubernetes allows you to specify a CPU request and a CPU limit, which means that, say you request 0.5 CPUs and then you set the limit at 1. That means that you will be guaranteed half a CPU, but you may be able to use up to 1 CPU as well. But then if the task tries to use more than 1 CPU, more than the limit, then it would be starved. Or possibly killed, depending on how Kubernetes handles that, which I don't remember for sure. That's also something that people have requested, but it's also become sort of a relatively minor thing, I think, because we found that with Kubernetes, it's actually better to just not specify a limit in most cases, because the way that works out then is that every task gets exactly the minimum amount of CPUs that it needs. But then if it needs to use more for some reason, it can reach for more, and there's no limit on how much it can reach for. And that tends to work out a little bit better than when you apply a limit, and then that could end up starving certain tasks when you didn't really need to. Maybe you had some extra CPU time that you could have doled out, but because you had this limit, it didn't work out. There's still some use cases here and there for having a limit. Some systems actually require you to have a limit. So that's another thing we're considering, which again, it's like, I think that request is a little bit more clear cut at this point. But again, just because it's a lower priority thing and we want to make sure that we don't break anything or cause any unintended effects, that one's been on the back burner a bit. But I just wanted to highlight that one as well, because those two PRs are kind of tied together.
Those ones are kind of fun, where like we can add this, but people might prematurely optimize. So actually, maybe it's better if we if we don't. That's cool.
Yeah.
So how does that? The next thing I've got on the list here is resource limits. What was it that you were just talking about? And is that different or the same, or how does that tie into this?
Yeah, this was all of these PRs are things that I worked on like right when I joined the company, and I was still new to the Nextflow code base, and I was trying all these different things. And I think this was one where I got these two mixed up, where I thought I could implement them both like with the same feature, and that got way too complicated. So I split them up, but it's still a little bit confusing. So what resource limits is about, the proposal is for a directive called resource limits. And this is meant to address basically this. So, and obviously you guys know about this in NF Core, you guys came up with this convention where you can specify a sort of a pipeline level. Well, it's not really a pipeline level, but you specify these resource limits like as pipeline params, like max CPUs, max memory, max time. And these limits represent the maximum amount of resources that any individual node in the system has. This is mainly pertinent for like HPC schedulers. So maybe you have your university cluster and you know that the beefiest node on your system has, 32 cores, 144 gigabytes of RAM, and, your max wall time on your system is 72 hours, right? So if you're using some like dynamic resource, like some kind of dynamic resource allocation strategy where you're saying like every time a task is retried, double the memory, double the CPUs, double the time. Obviously you don't want that to exceed, the system limits that you're under, right? Because then what usually happens in that case is that job will just never be scheduled. Some schedulers might be smart enough to say like, hey, this job is impossible to schedule, so I'm just going to fail it. But in my experience, the scheduler usually just lets it sit there forever. And so you guys came up with this convention to say like, hey, anytime you request the resources, run it through this check max function, which will check it against, the limits that you've provided and basically bump it down if it needs to, right? And so that means that every NF Core config file has this checkmax function in it, which is technically possible. I mean, people may not know this, but like Nextflow config files are basically just Groovy scripts with a little bit of extra syntax. So you can have functions, you can have all kinds of code, you can have if statements, you can put entire config blocks and if statements. This is the kind of stuff that makes Paulo cry because he's like, the config was never meant for this, but obviously people do what they need to do to get stuff to work, right? And so we've got this checkmax function floating around. And so this directive is intended to basically eliminate that, remove the need for it.
That both the request for this and also the NF Core code you're talking about lies with me, actually. So I have personal responsibility in making Paulo cry here. As you say, I mean, this is something we hit in the early days in NF Core, even maybe before NF Core. That check max function is not the piece of code I'm most proud of. But having said that, the fact that it's still there like 5 years on shows that it does work. But functionally it works. It sets a ceiling on the limits, but also it's one of the most poorly named functions I've ever written. And to the extent that we have like an autoresponder in NF Core now, which you can trigger, because so many people come in and say, I upped for check max, but the process is not using any more resources, and we're like, yeah, no, it's just the ceiling. It's just a fact. So if you want your pipeline to use more resources, changing this doesn't make any difference. It's just moving up the maximum. So it's badly named. It's a function in the config file, which is horrible. It's an extra wrap around every single resource request in the config file. There's just so many things about this that I don't like. So please, I'm really excited about getting us merged in so we can get rid of all that.
It's funny. It's so prevalent that when I implemented the resource optimization in Tower, there's actually a hidden param on the optimization service to add that checkmax function to the resource request. It's disabled by default, and it's basically like, I'm not going to add it unless people start asking for it. But I just had this premonition, like people are going to want something like this. So anyway,
Yeah.
but you know,
I was
it's
just
go ahead.
I was going to say I was just checking the original issue we've got here. Actually, this is the one I wrote, 2018. So that dates it a little bit. That's when I
Yeah.
put this in, and this is Nextflow issue 640, and we're up to what, like 4,500 now. So it's
Yeah,
pretty
you
early
know when the
request.
Nextflow issues in triple digits that it's an oldie.
Yeah.
Like at this point, it's basically this one, and then the one about the automatic cleanup. I think are the only ones that are still around. But you know, it's all part of the process. Like as you know, NF Core has been a really good proving ground for like, you know, finding the limits of Nextflow and coming up with like these patchwork sort of solutions, and then see if they last. You know, if they have longevity, and then if they do, you know, then let's try to find a way to put them in the Nextflow proper. You know, the NF Core template is like this sort of buffer that, you know, that we're always striving to make it as small as possible by just doing it in Nextflow, right? But
Exactly. I feel like it's sort of ever doing this, you know, we're sticking more stuff into it and at the same time trying to take things out of it to put into core Nextflow or put into plugins.
yeah, and so I think this checkmax function has more than proven itself in that regard. And so now it's just a matter of figuring out, you know, what's the best way to do that in Nextflow. And so what this PR does is it adds a directive called resourceLimits, and in its current implementation, the value of this directive is basically just a map, and then the keys of that map correspond to different like resource directives that you want to limit. So you would have, you know, resource limits, and then you'd have a map, and then, you know, if you want to limit the CPUs, you would say like CPUs colon, and then whatever, you know, whatever you would normally put as like max CPUs in your NF Core pipeline, you would just put that here. So yeah, what we're looking at on screen here is what that syntax looks like. You just have a directive, and then you have CPUs, memory, time. These will basically replace, you know, those NF Core params that people use. And then you can chuck out your checkmax function, because Nextflow will do that for you. So when you have these limits, every time that Nextflow tries to launch a task and it has to fetch the task resources, like, okay, get the task CPUs, memory, wall time, whatever. Every time it does that, it will go through this resource limits directive and, you know, bump it down if it exceeds that limit. So exactly what checkmax is doing. And yeah, hopefully that should simplify some things for people.
Yeah, and you came up with a better name as well.
I mean, it's still a little bit confusing because, you know, we've got resource limits, and because some, you know, because we've also got like the accelerator directive has the concept of a request and a limit. Although I think I don't think that ever really made sense. I think we added that in because of like Kubernetes supports that, but I don't really know a situation where you would have a task that definitely needs one GPU, but, you know, if you could throw 4 GPUs at it, that'd be cool too, because you can't just like, you know, like add and take away GPUs like on the fly, which is kind of how the request and limit in Kubernetes is supposed to work. That's kind of a tangent, but the point is like there's a separate concept of request and limit in Kubernetes. And what I was saying before about supporting a request and a limit for CPUs, but that's different from this because this is more like a pipeline level limit, right? So it still could get a little bit confusing, but I think it's about as good as it's going to get. I mean, with all of these PRs, I welcome you guys to go and check them out and provide feedback. You know, give your opinion on how things should work. But I think out of all of these, I think this resource limits directive is actually pretty solid. I wrote it a long time ago, and then it wasn't until I think like a month or two ago, I think Julia came by and we actually were able to test it. Which I hadn't really done. And so I fixed up a few things, got it working. So I think it's ready to go. If anybody wants to go on there and try it out, you're more than welcome to give feedback.
Very cool. Nice.
It's really cool. I just wanted to clarify as well, will this be at the pipeline level or a process level, or something that you can specify for like if you're sending your job to a specific server, for example?
So I guess that will be an advantage of this directive, is that what you saw in the in the screen share there was showing applying that directive to the entire pipeline, right? So that's matching the existing functionality of like checkmax, right? But then because it's a process directive, you could apply it to specific processes as well. I don't know what the use is for that. I'm sure somebody will find a reason to do that, but you can do that too.
Something that jumps to mind for me is you could stick this inside a profile, config profile. So then we've got like profile test, for example, which runs on GitHub Actions. And then it could still be at process level for the whole pipeline, but it'd be kind of bundled within a single profile. So then, Chris, you were saying different cluster. You could have, minus profile, my cluster, and have that set of resource limits set within that config profile.
That'd be great, actually, wouldn't it? Because a lot of times those limits are like cluster specific. So
exactly. I can't think of when you would want to specify it on a process level. So, some processes within a pipeline different to others, but it's possible.
Yeah, it's just I was wondering where those limits were, but it sounds like there's a lot of flexibility in it already, which is cool.
Yeah, I guess it's defined in a similar way to process.queue, or I think that's a process level directive. So then you can kind of pair the two together, I guess. Nice. Right, Ben, take us on to the next thing. Virtual threads.
Oh yeah, virtual threads. So yeah, this is a bit of a deep cut, I think, but maybe this is something some people can appreciate. So this is one of those things that people like to compare between different programming languages. Is like, well, what does their concurrency model look like? Like if you want to write a parallel program in Java or Python or Go or Node.js or whatever, like what does it look like to launch? Like can this language handle like 1 million threads, right? And so we've seen a lot of innovations across different languages in this. And virtual threads is basically Java's latest innovation. You could say it's basically catching up to what a lot of other languages have already done for a long time. But it's here now, and we're all happy for it. So basically, the way this works is that by default, when you use threads in a Java program, and I say Java because Nextflow is written in Groovy, but ultimately that gets compiled into a Java program, right? So when we're talking about Java, it's just as relevant to Nextflow as like anything in Groovy, right? So when you use threads normally in Java, basically that thread is called the OS or platform thread, and it's pretty heavyweight in terms of like its memory usage. It takes up at least a few megabytes, if not more. And so if you want to have a program where you say you're launching like 1,000 threads concurrently, that would not be very practical with platform threads, the default sort of threads that Java provides to you, just because they're so memory intensive. It really limits how many things you can have going on. So what Java introduced with virtual threads is basically what happens now is that a virtual thread is very lightweight in terms of memory usage. It's very small. And what happens is that Java, the JVM, creates like a sort of a pool of these platform threads. So probably like one per CPU or something like that, which is, a reasonable size. And then it has this separate pool of virtual threads, which could be, as many virtual threads as you want. You could probably get it to thousands or millions of them before you start like really using lots of memory, right? And all of those virtual threads will share this pool of platform threads, kind of in the same way that like, you have your operating system and maybe you have 8 CPU cores, but you could have like a bajillion different tasks running on your desktop or on your server or whatever. And the OS knows how to, divvy up the CPU time among all of those different processes or windows, right? It's much the same thing here with virtual threads. You have an arbitrary number of virtual threads sharing a small fixed pool of heavyweight platform threads, right? And so that allows you to be a little bit more, that allows you to do a few things with concurrency that you couldn't do before. One of the main use cases is if you have a bunch of threads that are very IO heavy. So maybe it's something like you're uploading data to S3 or downloading data, and you're not really using the CPU much to do that. So you have this thread that's just kind of sitting here and waiting for data to transfer, right? So it's very IO heavy, CPU lightweight. If you had like 1,000 of those threads, you could probably run them all in parallel, and you'd saturate your network interface, right? But your CPU would probably be pretty light, and it could be doing other things, or at least it could handle 1,000 threads that are using 0.01 CPU, right? And so this allows, whereas before, if you're using platform threads, you basically be limited by how much memory you have, right? It's like, well, I could upload 1,000 files at once, but I only have enough memory to support 100 threads doing this. So now, your memory's full, but your CPU's not doing a lot. And so it's kind of like arbitrary resource limit. And so with virtual threads now, basically we can have unlimited concurrency without being bottlenecked by, how much RAM we happen to have. And this has also been, sort of a topic of exploration with Nextflow, is like, well, how much memory do you actually need for the Nextflow head node? Like most of the time, 2 to 4 gigabytes of RAM is enough. But we've had cases where, Nextflow runs out of memory, like the head node runs out of memory. And it usually has to do with these like S3 transfers, like you're running a large pipeline and you have to like publish a ton of S3 files at the end. And sometimes Nextflow seems to run out of memory. I think we've actually fixed a lot of those issues last year. There was just like either some memory leaks or just the way that Nextflow was handling the S3 transfers in particular was just very inefficient. But there's still this limitation that we think we could unlock with virtual threads. So we initially thought this was something that we wouldn't be able to work on until at the end of this year. But it turns out it was actually quite easy to add to Nextflow. It was basically just like a switch you just have to enable. And so Paulo added it in several months ago, and then I've been benchmarking it over the past couple months on my spare time to like figure out if there's any benefit to it and where that benefit lies. We're hoping to publish a blog post or make an announcement at some point once we've concluded it. But I'll go ahead and share here what I found so far is that I think the place where it seems to help the most is when you have a pipeline that has a bunch of tasks and that has to publish a ton of files to S3 or some remote storage at the end of the pipeline. What you'll see sometimes with these pipeline runs is that it'll finish all the tasks and then it'll just be sitting there being like waiting for files to publish, like 1,000 left, 950 left, 900 left. And that process of waiting for all the files to actually be uploaded or even just transferred, like you might just be copying a file from one S3 bucket to another, right? But you're still waiting for that to happen. For a large pipeline, that can take hours. And we've actually had cases where, that thread manager, that thread pool that handles that would have like a timeout of like 12 hours, which, you'd think is like a reasonable amount of time. But some of these pipelines would take like days to publish all of their final outputs, and they would hit that timeout, and we'd have to tell them like, well, just increase it. But it's still kind of ridiculous that the pipeline is taking like 2 or 3 days to publish all of these files, and it's not a CPU intensive thing; it's an IO intensive thing. So you should be maxing out your IO interface, and if your network interface can handle more than your memory, then like there is available memory just to hold all these like heavy platform threads, then that's an unnecessary limitation, right? And so what I found with some basic tests, just some simple tests where I like upload a bunch of files to S3, is that when you turn on those virtual threads, you can significantly cut down on that publishing time. Now, how much savings you actually get with a real pipeline is going to vary a lot, and it's probably going to be a bit smaller than like those pure tests that I was seeing, where I think I can get as much as like 20 to 30% reduction of overall workflow runtime when it's just like purely uploading these files. But if you got a bunch of tasks and maybe you have a task. Maybe you have like this one final task that runs for several hours at the end, like some kind of summarizer task. Maybe Nextflow is able to upload all those files anyway while that one task is running, for instance. But we'll have to see. It certainly doesn't hurt to have virtual threads. So if nothing else, we may just enable it just so that the benefit is there. The benefit can be used when it's possible, and then otherwise it's not hurting anything. So
that's what I was going to ask next. So this pull request is merged, right? So this is already part of Nextflow, or at least an unreleased version. So does anyone have to do anything to use this, or is it just going to be on for every user all the time from now on? Is there any downside to having it switched on?
So you guys can go and look at the PR if you're interested. Basically, Paulo just added an environment variable that you can use to turn it on. The other thing is that you have to have a newer version of Java, because it was added in like Java 19. So you would have to upgrade your Java runtime to 19 or newer for it to work. Otherwise, it'll fail. And as far as I know, like from the testing that I've done so far, it doesn't seem to hurt anything. What I've observed is that in cases where Nextflow has to have a bunch of IO heavy threads, like publishing outputs, what happens is that with virtual threads, it uses a little bit more CPU and a little bit more memory, but at the same time, it's a lot quicker. So you're using a little more CPU memory in return for lower runtime, which I think I would almost always take that trade-off, right? Especially if you have CPU and memory to spare, well, why not make the most of it, right? That's maybe counterintuitive, because I was saying how virtual threads use less memory, right? But what we do then is that we use the same amount of memory and we just get more bang for our buck, right? So that's how that works.
Nice. Okay. So for now, dig out the pull request, flip on the feature switch with an environment variable and try it out. And hopefully before long, everyone will just get that benefit as long as you're running Java, a latest enough version of Java.
Mm-hmm.
Cool. So we've had fractional CPUs, we've had virtual threads. I'm kind of expecting you to say we're going to have imaginary threads next or something. We've definitely pushed the boundaries of my understanding of CPU usage. But the next one's kind of a bit different. WebAssembly. The last podcast episode, we had Paolo on and we talked all about, Marcel and I quizzed him about containers and Wave and everything at length. So we kind of got a recent history of all container background and Nextflow and stuff. Tell us a bit about WebAssembly. Where does this fit in the picture?
Yeah, I think I kind of just threw this one in here. I guess it's a little bit related. We got into talking about like containers and how Docker does CPU shares and all this stuff, but this is really just a completely different thing. But it's an interesting thing to talk about. And so all the other stuff, there's PRs, right? This one is like complete experimental phase. We haven't done anything with this. We're just sort of kind of curious, a little WebAssembly curious. And I really encourage people to just look into the history of WebAssembly, because it's a really interesting history, how it evolved. It started out as just like, hey, is there a way that we could take our JavaScript code that we're running in the browser and compile it down to some lower level thing so that it can be faster? Because like the whole world's using the web and everybody's having to rely on JavaScript, and it's not like the fastest language. I mean, it is. The V8 engine has a lot of impressive aspects to it, but still, it could be a lot faster if it knew about things like what types and things of that nature. And so initially, it was this really wacky thing where it was like, JavaScript doesn't actually have like a integer type. Everything is floats. And so they created this compiler that would like compile your JavaScript into something that was a little bit faster, where it would bitwise or every like numerical variable in your code with 0. So you would see like, X or 0 with everything. And apparently that was a little hack to like convert that number into an integer from a float. And so now you could be doing integer math instead of floating point math, which is a little bit faster. That's kind of where it started. Obviously, that's a little bit ridiculous when you look into that, but it had some benefits. Since then, it's expanded in scope tremendously. So now we're at the point where I think they've actually come up with like some kind of bytecode, for WebAssembly that pretty much all the browsers support now. So it's sort of like an intermediate representation. And there are a bunch of different compilers now, WebAssembly compilers, that support different languages where, it's like, okay, you get your WebAssembly compiler for Python, and then it'll compile your Python code into this WebAssembly bytecode, and then you can run that bytecode in your browser. But it's not just that. You could then run that bytecode by, you could just pick up a WebAssembly runtime, which you could think of like as an interpreter that can run WebAssembly bytecode. And then you can just run that anywhere. And so it's become sort of this like universal compiler / runtime where you can take any programming language for which there is a WebAssembly compiler and then compile that code into the WebAssembly bytecode. And then you pick whatever environment you want to run it in, be it, Intel CPU or ARM, Windows or Linux. I don't actually know which all platforms they support, but you find a WebAssembly runtime for that environment, and then you can run that bytecode. And then on top of that, you could have, say, like, you could write some Rust code, compile it down to WebAssembly. You have this WebAssembly module, and then you go over to some Python script you have, and there's like a library you can use in Python to run WebAssembly bytecode, like as part of your Python program. Now you can run that WebAssembly module that you wrote in Rust in your Python code. And you can do that in any direction, like from any language to another, as long as you can compile the first language into WebAssembly, and then in your other language, you can run that bytecode. And so it's created a lot of interesting possibilities, as you guys can probably imagine. Like, what if we just, what if like thinking about all of these like basic library modules that get rewritten in every different language, especially like security cryptography modules where like it's really important that you get that right. What if we just wrote it once in, Rust, or, pick some language that everybody would agree, like this is probably the best language for writing this security module in, compile it to WebAssembly, and then every other language just uses that WebAssembly module, right? Could be interesting possibility. Another possibility, which gets to why we're interested in it, is that it's sort of you can think of it as a lightweight alternative to containers, because it has basically all the same properties as a container, right? You can compile it from anywhere and then run it from anywhere, as long as you have a WASM runtime for that environment, much in the same way that like you can run a Docker container anywhere where you can run the Docker runtime, right? So it's like, well, what if Nextflow, instead of launching containers, you specified a WebAssembly module, and you'd have to have all the same infrastructure, right? You'd have to have some kind of registry where these modules are stored. You download the module, and then Nextflow, looks for some WASM runtime on your system. There's a bunch of them. There's WASMer, there's WASMtime, a couple others. And so you could say like, okay, use this WASM runtime and then run this WASM module. And then here's the task script as usual, right? But it'll just run it with that module. And then you don't have to deal with pulling all these container layers and, having this whole environment around this simple tool that you want to run, right? So we could get a lot of potential savings from that, because a lot of, especially like in the cloud, a lot of the VM startup time also consists of like just pulling these image layers, right, for the containers. So I think we can get a lot of efficiency out of that.
So correct. This is kind of, a lot of this is new to me. I think of WebAssembly as being, run software in a web browser, but like you say, this is more like a universal interpretation layer between any different language, which is kind of cool. But that last point you mentioned, where you say you don't have to download all the layers and stuff. So Are you saying, because I guess with Docker, you always sort of base everything on top of a base image, which typically has some kind of operating system. So are you saying that with WebAssembly, you don't necessarily have to ship the whole operating system, you just kind of ship the bytecode for the tool and it doesn't need everything else? Or
Yeah, you would need the bytecode for the tool, and then I guess you'd probably need the same for all of the dependencies that the tool is using. That's where it gets hairy, because then the question is like, well, how deep do I need to go down this dependency tree? Do I have to compile all of these library dependencies that the tool is using? Do I have to take like the standard C library and compile that into WebAssembly? Or does the WASM runtime already have some of that stuff built in? I don't fully understand. I don't know much about those aspects of it. But the question there is like, can we actually do it without having to basically recreate the Docker image? Because if you have to include all of these dependencies and in the process of that, you just end up, getting a blob that's half the size of the original Docker image. Well, then you're not saving all that much. So we'll just have to see. We haven't done any testing or experimentation with this. It's just literally like I and some others have read about WebAssembly and trying to understand some of these new capabilities that they're exploring. And I'm trying to think about like, what could it work with Nextflow? And, it might. But I would also point out there's lots of alternatives or, sort of similar solutions that could work as well. For one thing, Docker is actually experimenting with supporting a WASM runtime. So instead of just creating our own, maybe you could just use Docker and just enable some feature flag, and it would just do that for you. And maybe it could get savings for you. I think that was pretty smart on for their part, because that sort of preserves them a little bit, reduces a little bit of risk of being outcompeted by some alternative. Another point is that, like, another one of the reasons why I think WebAssembly seems valuable is for the composability aspect, which is that with containers, it's very difficult to compose a container with multiple tools, right? Usually we create a separate container for each tool. And if you wanted to combine those and say like, well, I need a container that has both of these tools, you would just have to create a new container from scratch, right? There's not an easy way to like add containers together. Whereas with WebAssembly, you could probably do something like that because it's just like packages. You could just compose them. You don't have to worry about this underlying OS layer. But we've kind of solved this problem now with Wave. And I imagine you guys probably talked about this in the last episode, where with Wave now, you can just specify the list of conda packages you want to use for a task, and then Wave can just build that container for you. And then Wave has this build cache on the back end, right? So if a ton of people are requesting the exact same composition of conda packages, then Wave can just pull what it's already built and then send that to you. So it can handle this pretty efficiently. Maybe this whole thing about WebAssembly won't be as important with something like that.
It's nice to approach the same problem from different angles, though. It's a cool idea to be able to just have these kind of, a library of runtimes and just mix and match. And, Nextflow has some prerequisites where it needs to be able to, run PS or whatever to get the usage metrics, and you need this metric, and you just kind of throw in any kind of different executables that you need to have in a runtime.
Yeah,
it feels kind of liberating after working with Docker and stuff for a while.
Yeah. So, but going just as far as like the feasibility of WebAssembly, I would still say it's at least a few years out, because I think it's really just going through like a process of maturation, because they're still trying to define all the sort of the standard APIs and like how do we support Windows, Linux, and Mac through sort of the same interface. How do we like make sure that people can have the same security guarantees that they would get with just compiling it directly. So it's probably going to be a little while before it's stable enough. Not only that, but also like the actual WASM compilers that are just sort of being developed here, there, and everywhere just by whoever can do it for all the different languages, right? So like Rust, Python, and Go, I think are all pretty well supported. And then Java there are some WASM compilers for Java, but I think they're not nearly as mature. I'm not sure about R. I'm trying to go through all the languages in which like bioinformatic tools are written in. So I think probably the main one is Java. Once Java has better support, then we'll probably have probably then you'll have full coverage where like almost all of your bioinformatics tools, no matter what language they're written in, could be compiled to WASM. You could probably do that now. You could probably just try it, and probably a lot of them would work, but you'd probably run into a lot of weird, edge cases, low-level issues that, would be very difficult to fix on your own, where it would be better to just wait for, the developers of those tools to fix them. So.
Very cool. I've been chatting a little bit recently to a guy behind sandbox.bio, which uses WebAssembly, and I think there's a project that he's involved in called BioWASM, which is like a repository of bioinformatics tools which have been compiled into WASM bytecode. So there's kind of like a Bioconda equivalent, I guess, but for WASM it started. I don't think it's got loads of tools. I'm just looking at the website now. There's BioWASM here. And I've got a list of packages here. So we're not talking about thousands of packages here, but you've got like bed tools and bowtie and stuff that's sort of ready to go. So a nascent community.
Yeah. It looks like his front page, it said C and C++ tools running in the browser. So maybe he's just doing that right now.
Yes, possible.
Because C and C++ have pretty good support for WebAssembly at this point. And a lot of tools are written in those languages. So.
And if you look at these bioinformatics tools like SAM tools and bed tools and stuff, I think those are mostly C.
Mm-hmm.
Good stuff. That was illuminating. I've learned a lot about WebAssembly now. It's good. I feel like I thought I had a pretty good idea about it, but it was definitely backfilling some history and also some possibilities there. It was pretty good.
Yeah, if anybody's interested, I encourage people to look. There's a video called "The Birth and Death of JavaScript," which this guy made, where he talks about WebAssembly, but it's partly fiction. So it's sort of a prediction of the future. It's a funny little story. I'd highly encourage people to check that out, because it is actually, despite the fictional aspects, it is a pretty good primer actually on how WebAssembly works. So
to dig it out and put it in the show notes.
Yeah.
Cool. All right, we should move on to the wrap up and talk about our kind of usual topics. Chris, we got any content that's new out on the websites this week?
I think it's only been one blog post since the last podcast. So this post is on the Sakira blog, and it was written by Adam, who's a scientific developer at Sakira. It's all about automating your pipeline execution with Nextflow and Tower. This is actually quite a nice read. It's not too long, but it really sort of explores some of the ways that you can sort of take executing your pipelines to the next level, so you don't just have to worry about building your pipeline anymore. Obviously, there's a lot of things that you need to worry about in terms of provisioning your compute and staging data, as well as creating containers. What this blog post does is really sort of walk you through a few different sort of features of Nextflow and Tower that can help you automate those tasks and save yourself a lot of time and prevent you from making mistakes and reducing costs and things like that. So it outlines some things like your Tower API, your Tower CLI, your TW kit, pipeline actions, cloud service integrations, automated pipeline recovery, automated notifications, and container management. And like I said, it's actually quite a nice wee read. So it takes 5-10 minutes to sort of flick through with some nice code snippets in there as well. So if that sounds like something that you're interested in, you can sort of jump through that as well.
I think I was joking about this article the other week when it came out, where I was like, I think Tower APIs might be mature enough now to where you could write a Nextflow pipeline that launches multiple Nextflow pipelines in sequence, one after the other, just by calling Tower. And then you could take that Nextflow pipeline and also launch it in Tower. So you could sort of create this loop between Nextflow and Tower to run just like a pipeline of pipelines and just go as big as you want.
I was going to say, see how many layers. It's Towerception.
Mm-hmm.
This is a nice article as well, because it comes back and touches on some topics we've had in earlier episodes of the podcast. We had an episode a little while ago, just at the end of the summer, where we had Evan and Harshal on, and we were talking about some of this automation stuff. We talked about the CLI, TW kit that's been renamed. That was at the time of that podcast called TW PyWrap, but it's the Python library, so you can import TW kit and then in a Python script or a notebook or whatever, and then kind of get at all of that underlying tower metadata and do actions within a Python script. So it's cool to see that. It's kind of matured a little bit, I think, since we chatted, and nice to see it written up as a blog post.
Mm-hmm.
And Ben, there's a hot topic that is right now, chaining pipelines. I've not heard that solution. It's a good one. We'll have to come back to this. I think it deserves half a podcast just in itself.
Exactly, another half podcast there at least.
Cool. Okay, so that's worth a read. Any events? We've just had the advanced training. I guess that was a few days ago. The first time we've run the public advanced training with Rob Simon.
Yep. So again, all of that's on YouTube. So it'll push us that onto YouTube. If it's not there already, it'll be very, very soon. It's quite a nice way of just sharing all these trainings with the community. You can go back and watch them at any time. And of course, jump onto the different channels on Slack or wherever else and ask questions. If there's anything that you want to sort of expand or have expanded in more detail. So do go check those out if there's something that interests you.
Yeah, I've got the event webpage up on the NF Core website. So if you can't remember anything else, just hit the NF Core website and click training. That's what I do. Good stuff. And then, of course, the summit, registration's closed, program's locked. Getting psyched. It's not long now. We've hit capacity for Boston, so we literally can't fit any more chairs into the venue, which is a nice place to be. Apologies to anyone who missed the deadline. So, but we've got a waiting list set up now, I think, in case there are any cancellations. But it's good to see so much enthusiasm.
Yeah, absolutely, and the program's looking really good as well. So I'm really psyched about it.
And get to see all your lovely faces in person for once as well. And Ben will be in the same time zone.
Oh yeah, I'm excited for it.
Great stuff. All right. Thanks everyone. Thanks for joining. Really appreciate your time, and thanks for coming and talking to us about the future of Nextflow, Ben. As always, it's been a pleasure.
Of course.
And yeah, thank you everyone for tuning in and listening to this episode of the channel's podcast. We'll see you in a couple of weeks. The next episode might actually be in the summit. So we have to figure out what we're going to do with that, whether we're going to live stream from a venue or what. But we haven't decided yet.
What could possibly go wrong?
Exactly. I'm not going to commit myself to anything. Good stuff. All right. Thanks very much, everybody. Speak to you next time.
Bye, everybody.
Bye.